I had some students come into my office asking for some help with just simplifying a circuit. And they said that really they could use with some more tutorial on it. So I'm going to start my loop analysis by first saying how you can solve a, quote, simple circuit by simplification. Now, this isn't going to be necessarily super easy, but it's easier than the other methods. So simplification of circuits means that we are going to be combining resistors in series and parallel to get a simpler circuit. Now, hopefully they're going to ask me, what is the current being supplied by the power supply here? They could have asked me how much current is going through this resistor. If they ask me how much current is going through the resistor labeled 3R, and I just put those in so I can have simple numbers, that's going to be harder. And so I'll go through and show how we would find what the current total is, and then go back and say, okay, so how would I find what I3 is specifically? So the first thing is I want to simplify this, so I want to find what things I have in series or parallel. And so when you look at this, you'll probably note that I have these, let me make a square box here. Okay, it won't be a square, but it'll be a box. I have these 4 resistors that are all in parallel. And then those are in series with the one above it, 3R. And then that combination of 3R and the parallel ones is in parallel with the series combination of 2R and 4R. So I need to go through this and just define, okay, what can I simplify and go piece by piece. So I'm going to start by doing 2 pieces. I am first going to say R equivalent 1 is the equivalent resistance of the 4 resistors in parallel. And so using our resistors in parallel equation, I'm going to write over here the equation for adding resistors in parallel. 1 over resistance equivalent parallel is equal to 1 over R1 plus 1 over R2 plus 1 over R3, ... for as many as you have. So I have that equation, so I'm just going to have here 1 divided by R equivalent 1. And remember, it's everything that's inside of that rectangle, the blue rectangle. So that's just going to be 1 over 5R plus 1 over 6R plus 1 over 7R plus 1 over 8R, which is equal to, well, they all have 1 over R in them, and I have 1/5 plus 1/6 plus 1/7 plus 1/8. Now, as far as simplification goes, there isn't a lot of simplification I can do on this. I'm going to have 1 over R times, and on top I'll have the sum of these numbers, 5 plus 6 plus, actually no, I won't have that out. Now will I? I will have something crazy on top, and I haven't pre-calculated this, so I have to do it manually. I'm going to need more space, so let me put it down below. 1 over R times, I'm just going to multiply everything by 5 times 6 times 7 times 8. So on the bottom, I'm going to have 5 times 6 times 7 times 8, which is 30 times 7, 210 times 8, 1, 6, 8, 0. And on top, the first one is 6 times 7 times 8, which is, man, I've got to get a calculator. 56 times 6. 6 times 5 is 30. 336. The next one, 5 times 7 times 8. 5 times 8 is 40. That's 280. Plus the next one, 5 times 6 times 8. That's going to be 5 times 8 is 40, times 6 is 240. And the last one, 5 times 6 times 7. That's going to be 30 times 7 is 210. And if I did those numbers correctly, I am actually going to at least do the first one on my calculator just because I'm not fully convinced that I am faultless. Okay, that was right. And plus 240 plus 210. So that gives me 1 over r times 1066 divided by Yep, 1680. So R equivalent 1 is equal to R times 1680 divided by 1066. I'm going to leave it like, actually, no, I'm going to go ahead and convert that right now to a decimal value. And I will keep just 4 digits. So that's 1 point. Actually, I'll keep 4 decimal places, 5 digits. Equals R times 1.5760. So that's the value for the R equivalent 1. Now I'm going to change to green, and I'm also going to combine those resistors into R equivalent 2. So R equivalent 2 is the series combination of 2R and 3R. Well, R series equivalent is equal to R1 plus R2 plus R3 plus dot dot dot. So in this case, I just have 2. That's going to be 2R plus 4R equals 6R. While I love to do series so much more than I love to do parallel. Okay, so now I've made 2 simplifications, so let me redraw the circuit. So my circuit is now, I still have my battery. How do I know it's a battery? Because it has 2 cells. And I'm going to use color coding of a sort here just so we can be clear on what I've done in the previous steps. So the blue is the R equivalent 1, and the green is the R equivalent 2. And then, of course, I still have the 1R. That was not what color I intended. The 1R and 3R that I had in my original circuit. So now looking at this, I see that I have 3R and R equivalent 1 are in series. So I will go ahead and now that I feel comfortable, I will consider 2 steps in one. That is, I am going to combine all of these resistors in one step. The 3R and the R equivalent 1 are in series, so I can do that straightforward, and then those are in parallel with R equivalent 2. So I'm going to have, forgot to put the 12 volts. So I'm going to have R equivalent 3 is the red box, so parallel, so I have to use the parallel equation. 1 over R equivalent 3 is 1 over 3R plus R equivalent 1. Those two are in series, so I have to put those like that. Plus 1 over R equivalent 2. So that's equal to 1 over 3R. Well, that's a funny looking R. 3R plus 1.5760R plus 1 over 6R. Or simplifying, that's 1 over R times 1 over 4.5760 plus 1 over 6. Now for this here, of course, I am just going to use a calculator. I am in no way able to do those fractions in my head. And so bear with me for just a second. So 1 over R equivalent 3 is 0.38520 divided by R. Well, take the inverse of that, and I have R equivalent 3 is equal to 2.5961 R. So now that I've gotten this far, my circuit is very simple. My circuit is now just my 12-volt battery with 1R here, and then I have my R equivalent 3 equals 2.5961R there. So given that this is 12 volts, I now know that I have a, whoops, that's showing you what's coming next. I have a resistance total that's equal to the sum of those two in series, which once again, I can just do this one. I don't need to write out 1R plus 2.5961R. They're in series, you just add them together, and that's 3.5961R. So the current that is flowing out of my battery using Ohm's law is going to be the voltage of my battery divided by the total resistance. So 12 volts divided by 3.5961 R. Now, of course, I didn't define what R was. Let's make life easy and say R is equal to 1 ohm. That will make the calculation very straightforward. And I'll have my current is equal to just 12 volts over 596, not 69. So just take 12 divided by 3.5961, and I have 3.3370 amps. Now, I have found the entire current. What if I wanted to go back and find what the current was that I labeled I3 here? Well, to find I3, I'm going to have to first determine how much voltage I have in my drop across the 1 ohm resistor. And then with that voltage, it goes through my R equivalent 1 plus 3R. So now I'm going to have to put in a new page for this. You already saw that I've got something already on the next page. So if I want to find the current through R3, I have to bring my circuit back at least to this state. So I'm going to replace 1R with 1 ohm, 3 ohms, and then I have my equivalent resistance here that was, and I don't remember sadly, I know I was just there, 1.5760 ohms. And then I had another equivalent resistance here that was 6 ohms. So now I know I start with 12 volts here, and I have a current of 3.3370 amperes flowing through. So if I started, let's say this is my reference point. So I'll put my ground there. That means it's my reference point. If I start 0 here, I go up 12. If the current's going that direction, then using our sign conventions, the energy per charge, the voltage, had to drop. So I started higher and went down, and the voltage drop is equal to IR, which in this case is 3.3370 amps times 1 ohm equals 3.3370 volts. So I go up 12 and then I drop 3.3370. Well, 12 volts minus 3.3370 volts is equal to 8.6630 volts. So that means the voltage right here is 8.6630 volts. Now there are two ways to go from here. I could calculate the current here and the current, and then get this current by using Kirchhoff's current law, or I can just do it the direct route, and I will do it the direct route. So I now have this I3 that goes through my 3 ohm resistor and the parallel group of R equivalent 1. Just be glad that I didn't ask what's the current through one of the single resistors in the R equivalent 1. So in that case, I can just say I3 is equal to, I'm taking Ohm's law and solving for I, it's equal to the voltage drop, 8.6630 volts, divided by the total resistance in that branch. A branch is a term we use going from one essential node to another essential node. So this is a branch, there's another branch. As an essential node is where 3 or more elements meet. So that total resistance, 3 plus 1.57, is 4.15760 ohms. And so I just take my 8.663 and I divide by 4.15760, and I have 2.0837 amps. And of course, now that I know the current here is 2.0837 amps and the total was 3.370 amps, I could go ahead and just use Kirchhoff's current law to say that the current over here, that I'll call I2 since it went through resistor 2, is I minus I3, so 3.3370 amps minus 2.0837 amps, which is 1.2533 amps. Or I could have done I2 is equal to the voltage across I2, which is again 8.6630 volts, divided by that resistance of 6 ohms. And I'm just double checking. Uh-oh. And this is a sign that I made a mistake somewhere, because I don't get the same thing. Uh-oh. I got 1.4438 amps. Okay, so now we can see I made a mistake. Where did I make a mistake? Can't rightly tell you. This is, of course, one of the problems you have with doing these kind of problems. There's a lot of math. I did a lot of the math in my head. It's most likely that I made my mistake up here calculating R equivalent 1. That's the most likely scenario. I can't right now in any timely fashion go through and tell you where I made the mistake. But we know that I made a mistake because I calculate 2 different ways and I get 2 different answers. There can only be one answer, so you know that there's a mistake. I'm sorry that I didn't do it perfectly the first time. I will come back and tell you in class what I did wrong. Okay, moving on. The second step here, loop analysis using Kirchhoff's laws. Now, usually in a circuit class, we talk about mesh analysis. Here I use the term loop analysis for a very specific reason, because mesh analysis really is a more refined method, which I will talk about at the very end of this tutorial. So what is loop analysis using Kirchhoff's laws and Ohm's law? First, we only have 3 equations we have to use. We have to use sum of the voltages on a loop equals 0, what we call Kirchhoff's voltage law or the loop law. And then we have sum of the currents at a node is equal to 0, what we call Kirchhoff's current law or the junction law. And then we have the voltage drop is equal to IR, which of course is Georg Ohm's law. So we're going to use those 3 equations. So we take a circuit, and so let me just draw a simple circuit here. My circuit will have a battery here. Whoops, missed one stroke. A battery here, a resistor here, a battery here, a resistor here, and a resistor here, and for good measure, a resistor here. So I'm going to make these 6 volts, 10 volts, and 3 ohms, 6 ohms, 2 ohms, and 12 ohms. Okay, when you start the circuit, the first thing I'm going to do is I am going to make all the loop equations I can. So if I'm going to make loop equations, I have to start by identifying my loops. So I'm going to identify every loop and I'll give it a name. So I'll call this here loop 1. This here loop 2. This here loop 3. Now there are a few more loops than I'm showing here, but I'm going to show a 4th loop that goes all the way around the outside that I'll call loop 4. And so let's make the equations for each one of these. So I'm going to have, for loop 1, loop means I'm going to use the loop law, the sum of the voltages on the loop equals 0. Now, to make sure I don't get confused, I always start at the bottom left-hand corner of my circuit. So I'm going to start here, and if I start there and go up, I went from the negative side to the positive side of the battery. Remember, short side of the battery is the negative, long side is the positive. So that means I went up 6 volts there. So I'm going to have a plus 6 volts because I went up 6 volts. Next, I come to my 3 ohm resistor. I don't know what the voltage is there, right? But I have not defined, and this is a very important step that I should have done and didn't. When you're making a circuit, you need to define the current through each element. So I'm going to put a current here that I'm going to call I1. Now, this is in series with this 6 volt power supply. And elements that are in series have to have the same current. So I'm going to mark the current here, and I'm going to call that I1 as well, because it's going in the same branch. Remember I said earlier, about 5 minutes ago, that a branch is connecting from essential node to essential node. Okay, so that's my current 1. I have this power supply here. I'm going to draw a current like this and call that current 2. Now notice current 2 is not in series with the 6 ohm resistor. Current 1 and current 2 combine here at this node and come together for the 6 ohm resistor, so I'm going to call this I3. Now I have 2 more to go. I am just going to guess, and I think I'm guessing wrong. Call this I4 and this I5. Now that I've identified all of the currents, I immediately go through and say which side's positive and which side's negative for each one. So for a resistor, the side with the tail is the positive, the side with the head is the negative. So I have the voltages, the positive and negative for each resistor marked. For the power supplies, of course, the plus and minus go, like I said before, with the long and the short sides. Now notice the current has the opposite convention. The plus is with the head of the arrow for the power supply. That's because the power supply should be supplying energy, supplying power. Whereas the resistor is absorbing power, absorbing energy. Remember, power is just the rate at which energy is being converted. And so that's why the arrows are different. So now that I've done that, I will continue on with my analysis. So I started at the bottom left corner, went up 6 volts. Now I can look at my signs and say, okay, that's going down. So a minus sign. And I don't know what the voltage is, but I use Ohm's law. So I just say, that's I1 multiplied by 3 ohms. Continuing on loop 1, it goes down through this power supply. So going from plus to minus means I'm dropping a minus 10 volts. Then I'm going through the 2 ohm resistor to get back to where I started, going from plus to minus. So minus, and that's I4 times 2 ohms. So there I have a complete equation. 0 equals all of this stuff. I started and ended the same place. I have completed Kirchhoff's voltage law. Loop 2. Sum of the voltages on the loop is equal to 0, which is equal to, so I'm going to once again start at the bottom left corner, go up, so that went up 10 volts, so plus 10 volts. Come over, going from plus to minus, so down. I don't know what that voltage is, so I just use Ohm's law again, so that's I3 times 6 ohms. And then I'm back where I started. So that's the end of it. That was a very short, simple equation. In fact, if you look at that, I can calculate I3 right now. That has only one unknown. Now I'm going to not do that. I'm going to keep going. But you can see that I3 is immediately known. Go to loop 3. Loop 3, I'll start here, going up. No change. Now I'm going against the current. I'm going up. So I have some of the voltages on the loop equals 0 equals plus I4 times 2 ohms. And then I come here, keep coming around, and now I'm going with the current arrow, going from plus to minus, so minus I5 times 12 ohms. And for my last loop, the one that's on the outside, I'll start here, at the bottom. I go up 6 volts, minus I1 times 3 ohms, minus I3 times 6 ohms, minus I5 times 12 ohms. And that's that equation. Now that's 4 equations. I could have made 2 more equations. I could have made a total of 6, but I'm going to show you something here that's really important. If you look at my circuit, how many unknowns do I have? Well, they're the purple currents, so my unknowns are going to be I1, I2, I3, I4, I5. Now, a very, very simple rule for solving equations. You need as many equations as you have unknowns if you're going to solve for all of the unknowns. So I need a total of 5 equations because I have 5 unknowns. These equations need to be independent. That is, I can't have 2 or 3 equations that are really repeating themselves. And if you look at these equations I have, you might have noticed something peculiar. If I add up the first 3, if I take equation 1 plus equation 2 plus equation 3, I'll have the 6 volts, minus I3 2, or I1 times 3 ohms, minus I1 3 ohms, minus 10 ohms plus 10 ohms, so those two are going to subtract out if I add them together. And then minus I4 2 ohms, and this one here plus I4 2 ohms, so those are going to add out. Minus I3 times 6 ohms, minus I5 times 12 ohms. This final equation here is simply equation 1 plus equation 2 plus equation 3. So I can't use all 4 of these equations because this one here is redundant. It's a repeat of what I had before. So it's not independent. And if I had made the other 2, they also would have been not independent. So here's a rule on the loop equations. You can have number of independent loop equations is equal to the number of meshes. So what's a mesh? Or a mess, as my students often say. A mesh is the smallest circles you can make. So loops 1, 2, and 3 are 3 meshes. So I can have 3 independent mesh equations as long as I cover the entire circuit and have, well, let me not say and have. I have to cover the entire circuit and have the number of independent loop equations equal to the number of meshes. What's the easiest way to ensure that you have those 2 conditions met? Just use the meshes. If you make a loop equation for each of the meshes, you will have all of the independent equations you can have, and they will be all independent. The reason you have to cover the entire circuit is if I skipped a part of the circuit, I would have my equations not independent even when I used the number of meshes because I didn't cover everything. I covered some areas too much. So I have 3 independent equations, but I need a total of 5. So I go to my next analysis, the current. So Kirchhoff's current law is analysis of the nodes. Now, we need to identify all of our essential nodes. Remember, I've been talking about the difference in an essential node and a node. A node is where 2 elements or more meet. An essential node is where 3 or more meet. So if we look here, this corner, that's a node, but that's not an essential node. There are only 2 things that meet, this battery and that resistor. So the battery and resistor, they have to have the same current. It's true, but it's also trivial. So we don't consider that essential. It's trivial node. But over here, I have a node. All of this is one node that's connecting 1, 2, 3 elements. That's an essential node. So I'm going to label this node A. Here's another essential node. It's connecting 1, 2, 3 elements. I'm going to label that node B. And here I have my final essential node connecting this resistor, this power supply, this resistor, and this resistor, so 4 things. And I'm going to call that node C. So I have 3 nodes. 3 nodes. So let's make our node equations. So at node A, the sum of the currents at the node is equal to 0. Now I have to simply decide on my sign convention. Do I want currents coming in to be positive or currents leaving positive? Frankly, it doesn't matter. So I am just going to go ahead and say if it's coming in, it's positive. If it's leaving, it's negative. So if I look at node A, looking at the arrows I drew, I1 is coming in, I2 is coming in, and I3 is leaving. So using my sign convention, that's going to be I1 plus I2 minus I3. You see the node equations are much easier. B, sum of the currents in the node equals 0. So let's look at node B. At node B, I have I5 is coming in, I4 is coming in, and I1 is leaving. So it'll be I4 plus I5 minus I1. And finally at node C, I have I3 coming in and I2, 4, and 5 all leaving. I gotta check the numbers again. I3 is entering, 2, 4, and 5 are leaving. So there I have 3 equations. Now remember, how many total equations do I need? 5. How many did I have for my meshes? 3. So I only need 2 here. Which 2 do I take? It does not matter, but there is another important selection criteria. For independent equations, they have to be independent. The number of essential nodes minus 1 is, I should use the same format as before, equals number of independent node equations. Okay, I put them in opposite order. Should have put number of independent node equations equals number of essential nodes minus 1. So I had 3 essential nodes. Only 2 of these are independent. Once again, you'll see if I took the top equation plus the second equation, I'd have I1 minus I1, I2 minus I3 plus I4 plus I5. That was positive I2, I4, and 5. This was negative I2, I4, and 5. Negative I3, this was positive I3. You might say, wait, those are all the opposite signs. Well, but it's equal to 0. So if I multiply, if I take A plus B, that's equal to minus C. And so I have to get rid of one of them. And so I'll just randomly choose one and say this one is not independent. So now I have 3 equations. My meshes, that's my loops 1, 2, and 3, and my nodes. And now I have to solve this set of 5 equations with 5 unknowns. Now solving that set of equations with 5 equations and 5 unknowns, that is no simple task. And so I am going to invoke some linear algebra. So I'm going to spend a little time explaining a simple linear algebra technique that makes life a lot easier. But first I need to summarize these equations. And so to summarize them, I'm just going to do the copy and paste routine. Copy this. Copy. And go to the next page that I created. Paste from clipboard. So there's that. And then I have the mesh equations that we just did. Copy those, come down here and paste those. And so there are my 5 equations. Now I'm going to rewrite the equations in an organized fashion. I'm going to put them like this. Draw sesame. I'm going to put them so I have current 1, current 2, current 3, current 4, current 5, and equals the result. Sorry about that. So my first equation is going to be, current 1 here was negative 3 times current 1. There was no current 2, so I'm just going to put a plus 0. There was no current 3, so I'm going to put a plus 0. Current 4 was minus 2 ohms. I'm going to put a plus parenthesis minus 2 ohms, current 4. There's no current 5. And that's equal to, because it's equal, I have to move the 6 volts to the other side by subtracting, so minus 6 volts. Second equation, well, the only thing it has on the one side is I3, so it's going to be 0 plus 0 plus, okay, plus a parenthesis minus 6 ohms, I3 plus 0 equals, move the 10 volts across, minus 10 volts. Next equation only has 4 and 5, so 0 plus 0 plus 0. 4 is positive, plus 2 ohms, I4, plus minus 12 ohms, I5, and that equals 0. So there I've rewritten all those equations in this format. These final equations are simpler to write. That's going to be I1, 1 times I1, plus 1 times I2, plus minus 1 times I3, plus 0 equals 0. And the final one is minus 1 times I1, plus 0 plus 1 times I4, plus 1, circled the wrong, or put parentheses around the wrong thing. Now, those are kind of squished, so I am going to, once again, rewrite them, spreading it out a little bit. I want to do them here so you could see the equations translating, but rewriting those, I have minus 3 ohms times I1, zero times I1, 0 times I1, okay, so now I put the i's in parentheses, just changing which one I had in parentheses. So that's my first set. For the second set, I have 0, 0, 0, 1, 0. So 0, 0. For I3s, I had 0, minus 6, minus 1, and 0. For I4s, it was minus 2 I4 plus 0 plus 2 I4 plus 0 plus 1 I4. And next to last for the 5s, it's plus 0 plus 0 minus 12 I5 plus 0 plus 1 I5. And then each one has equal. And then my answers were minus 6, minus 10, 0, 0, 0. Now you might wonder, why am I spending so much time writing this out in this long fashion? The reason is because using linear algebra, we can solve this set of 5 equations with 5 unknowns very simply. And you're probably saying, how, oh pray tell, can I solve this set of 5 equations easily? Well, all I have to do is take first how we write an equation with linear algebra. You probably have seen column and row vectors. In fact, we talk about vectors a lot in physics. And so we can make a column vector that has all of the coefficients of the i's. So for my first equation, that would be minus 3. Sorry. Minus 3 ohms, comma, 0, comma, 0, comma, minus 2 ohms, comma, 0. And then if I multiply that, okay, that's a row vector, by column vector I1, I2, I3, I4, I5, that will equal this times first thing in the row vector times the first thing in the column vector. So that's going to be minus 3 ohms times I1, second thing in the row times second thing in the column, so that's plus 0. Third thing, plus 0. Fourth thing, plus a minus 2 ohms times I4. And then the final thing, plus 0. So this is a way of writing an equation. Now this was equal to 0 because, well, not equal to 0, it doesn't have an equal sign. So I take this and I look, and what I just did was I exactly recreated that first equation. Now if I want to make the second equation, I could just put another column vector here. And for the second equation, it would be 0, comma, 0, comma, minus 6 ohms, comma, 0, comma, 0. And now, if I multiply these, I'll get 2 different equations. The second equation would be 0 plus 0 minus 6 ohms. Well, let's put a plus parenthesis. So that's what I get for the second equation. And so I have 2 equations, so I have now a column vector with 2 entries. Well, I have 5 equations, so I'm going to need to put in all 5 of my pieces of information here. So just reading from what I did above, the next one is going to be, and of course we usually don't show the commas at this point, we just show the values. So the next one is going to be 0, 0, 0, 2 ohms and minus 12 ohms. The next one, 1, 1, minus 1, 0, 0. And the final one, minus 1, 0, 0, 1, 1. And let me erase this. Instead of putting all of the equations out here, let me put what the answers are, because we know what the answers are to each one of these. The answer to the first equation was minus 6. The answer to this, minus 6 volts to be honest. The answer to the second one was minus 10 volts. And the third, fourth, and fifths were all 0. So now I have a linear algebra representation of that set of equations. And you're still, at this point, probably wondering, so what? What good is it? How is it going to make life easier for me? Well, here's how it makes life easier. Let us say that I call the first portion of this, which I am now going to color red. Let's say that I name that. I'm going to call that matrix A. And this column vector, I'm going to call vector I. Now, I don't know the numbers for I. And then the third vector, I will color it blue and call it, I'll call it B for blue. So what I have now is an equation that says, and of course excuse it's not going to be color coordinated at this point, matrix A multiplied by column vector I is equal to column vector B. Now you look at that and you say, okay, I've just about had enough. We've done a lot of work and we haven't gotten anywhere. Well, here's the key. If the equations are independent, then an inverse matrix A minus 1 exists. Okay, you're now totally fed up. What good is that? Well, as with any inverse, if I multiply here by A minus 1, I'm going to have something special. What I do to the left-hand side, I have to do the right-hand side of the equation, so I have to do it on both sides. So I multiplied A minus 1, that's the inverse of A, times A. But the inverse of A times A is always the unit vector, or the unit matrix. What's the unit matrix? For a 5 by 5, that's, well, it's all diagonal elements are 1, all the rest are 0. Well, if you multiply that through, that's just going to be equal to I1, I2, I3, I4, I5. So if I multiply both sides by the inverse matrix, I will have the answer as my column vector of the currents. But on the right-hand side, I had all numbers for my matrix A and all numbers for my column vector B. So my inverse matrix is all numbers. My column vector B is all numbers. I'm going to actually have values for these. And so when I do this, I will get my values for the problem simply by putting them in the matrix and doing the math. And, okay, how many of you can do the math? I'm looking around. No one's raising their hand. Of course, there's no one here, but I get the picture. You can't do the math. You probably don't know how to find the inverse matrix. I'm sure we did it in high school math, but that's been a long time, especially for me. But there is this function on your calculator called row reduction echelon form, RREF. And if you put RREF and then you put in the matrix A combined with, okay, I don't know how to write combined with, the column vector B, it will give you the unit matrix and the currents. And so I have to actually do a separate recording to show you how to do that. So I'm going to end this tutorial here so I can go straight to that and show you how to do that final portion. So I'll see you on the next recording.